problem is that in doing such a short module is that sometimes you get very little information to actually grasp some of the concepts. I'm going to try this and let's see how it goes. So 1 hour, usually it's a semester long course, and it's easy to kind of engage with some of these topics. So let's start by just watching a video. The reason I wanted to start with this is that when you normally think about acoustics, you really think more about bird song. But the reality is that there are different kinds of acoustics, and they all need not be produced just with the vocal track. So this example is a classic example of something that is just produced with feathers, right? But all of it kind of falls within this sexual selection kind of framework that Suhail was talking about. So that is one of the ideas. So what I'm going to talk to you about is to just dial back again and to think about how let's say just acoustic communication, how does it work, right? So you generally have a source that is some organism that is making the sound. So can I ask you, why do you think what is the purpose of vocalization? What are some different ideas that all of you have? Sorry?
Attention.
Sorry?
To gain attention.
Attention for what?
Mating purposes.
Huh?
Mating.
Mating purpose. So let's say attract mates. Okay, yeah, fine. Anything else?
Communication. I like to communicate.
Yeah, communication. Let's talk about a purpose.
Territory.
Territoriality. Okay, for some maintaining territories. Yeah.
It will act as a signal from some characters or like that.
Sorry, that's
Alarm, like
It will
alarm.
act as a
alarm. Yeah. So signal for, let's say, some presence of predators, right? What was that?
it will act like a signal of the character of the source bird.
Oh, yeah, that's a really good one. Okay, so so there is some assessment of quality of the individual, right? So that's a little bit more than it's kind of a combination of that territory stuff that's happening and also the sexual selection, attracting the mate. So how does that happen? It happens because there is some signal in this, in the way this communication happens, that the receiver is able to actually understand. Yeah. Anything else that you can think of other than these few?
So pair bonding. For pair bonding.
What do you mean by pair bonding?
Like male and female sometimes they sing together.
Okay. Yeah.
Signaling from Brown for chick.
Yeah, so that is a specific that is another kind of vocalization, yes. So for, they have these begging calls and things like that also, right? So you can think of various kinds of contexts and reasons for which there is this, communication, acoustic communication is used. So there is a source and then there is a receiver, right? So in general, you would say that, okay, so the source is making some specific sounds, and then the hope is that the receiver actually is able to receive it fairly accurately, because you need to interpret whether this is a begging call, is it an alarm call, does it actually signal the quality of the individual, right? So like how well the signal is transmitted is one part of the problem. So ideally you want this to happen, but there are several problems that happen in between. Yeah? So can you think of some simple things that can go wrong in this process?
Interference.
Yeah, like what kind of?
Other noise, sound interference.
Okay, so there can be other sounds that kind of mask the presence of the original signal.
Direction of air.
Wind direction, yeah, that can happen. So, what happens with vegetation? Yeah, so there can be a lot of effects because of the kind of vegetation there is, right? So can anybody elaborate on that? What kind of habitat, what may happen in an open habitat, and what can happen in a forest habitat?
It's easy for the sound to propagate when vegetation is less dense, but if the vegetation is
I can't see where that is coming from. Yeah, okay, yeah.
So
No, just you just have to raise your hand, that's fine, yeah.
So when the vegetation is more dense, it's
Yeah.
difficult for sound to pass through.
Okay,
It has to go through many layers,
yeah.
and if the vegetation is less dense, probably it's easier.
Does everybody agree? Anybody who disagrees with that? Yeah.
Formation of echo.
What happened? Like,
Dense vegetation, sound may
yeah.
multiple times.
Okay.
You can get miscommunicated.
Okay. That is. So you're saying that it's not entirely true what she's saying. You just have some disagreement with what she's saying. Okay. Any other points?
But then there's also the fact that echolocation works for substitution.
Oh, echolocation. Okay, that's also slightly complicated. Okay, okay, let me. Yeah, the problem is that with this there are so many directions we can go. So now I'm going to try and channel it in a slightly different way. We will try to get to what you guys brought up by the end of this 1 hour talk, and let's hope we get there. But again, there is a lot of let's say a lot of information in these acoustic properties. Okay, so why do they need to use acoustics? So you can use this for like slightly, let's say, longer range communication. I mean, it need not be just in immediate line of sight. Yeah. So with that, there is an idea of space. So sound kind of, let's say, transmits farther. So how does this actually work out in terms of individuals and populations and so on? Because if we think of acoustic characters as some kind of traits, then you can think that there is variation in the traits, right? And there has to be individual variation for a female to select one, say, okay, this is a really very variable song or something. There has to be some basis of selection, right? So there is some inherent individual variation, let's say, but then that varies with space. And how that happens is actually something that I want to talk about a little bit more. But before I start, I just want to say that there's a lot of literature and there's a lot of research on the neurobiology, and the brain-connected things about song. So a lot of it is, a lot of songs, song types are very tightly related to a lot of neuro kind of processes. And we are really not talking about those. We are talking about some kind of an evolutionary and ecological effects of vocalization and relationships with that. So having said that, I want you to familiarize first with the idea of a spectrogram. How many of you know what a spectrogram is? Okay, no problem. So the simple thing, so this is actually, these are two different views, let's say, and this one is what we call the spectrogram, okay, the lower one. What you have on the x-axis is time, and what you have on the y-axis is frequency, okay? But this window on the top is a different representation of the same data, but what you can see here, the peaks is amplitude, so that is how loud it is. So with this you can tell that, okay, as this kind of call is going forward, the amplitude is kind of decreasing. Yeah? And you can't really tell that from this, except that it becomes a little bit lighter as it goes towards here. It's very dark and it keeps going lighter. Yeah? So what I want you to kind of understand here is that the relationship between frequency and amplitude. So you can be at the same frequency but have different amplitude. Okay? And for all the purposes of this talk, we are not really going to talk much about amplitude, but more about frequency and its distribution with time. Okay, so you just need to look at these patterns. Yeah, and on the y-axis is frequency. So that's high frequency. This is low frequency. Okay, and this is kilohertz, and human hearing is.
20 to 30.
Okay. So it's about. It looks like most of you know, right? All right. So I have another view of a spectrogram. This one is from this bird Sholicola, and you can see the relationship between the waveform and this one, right? The spectrogram. So this is like these are called trills, and they're these very short things which are repeated. So it's the same frequency, very similar, and it just goes tuck 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 tuck. It just repeats that same thing. Okay. All right. So the question is how these songs form and how are they kind of transmitted. There is a physical transmission part that we were beginning to talk about, and that I'm going to pause for now. We will pick that up later. But how, in terms of ecology and evolution, how do these songs work? Okay. So this, now that you know what spectrograms look like, this is a flycatcher. So the thing is that bird song is like human language, where an individual learns songs from its parents. It also learns from its neighbors. Okay, so this is slightly different from a regular genetic inheritance pathway, because there is some learning that is cultural. So unfortunately, or as it turns out, some groups of birds do not learn song, and this particular species, Eastern Phoebe, is and it's actually called Phoebe because it sounds like that. And how do you test for this? How do they know that it doesn't have a learned song? It's because if you isolate this bird, so you take a young one and you set it aside, and it doesn't interact with its parents, and it still sings pretty much the same song. You can also deafen the bird so that it can't hear itself sing, and it still sings pretty much the same song. I mean, more or less, right? So this is remarkable. So basically, there are some kinds of birds that have some innate songs, and in general, many subausine birds, if you remember from Anand's class, subausine birds, so many subausine birds don't really imitate other birds. They have a lot of innate songs. But having said that, there are plenty of exceptions. And this is another species. It's called the three-wattled bell bird. You can see the wattles there. Although they are kind of very closely related to other species that are not really learners, it has a geographic variation. So what you see here is a particular population, and you have to be able to kind of, I don't know if I have the song here. No, I don't have the song, but I have the song for a few other species. The problem with having songs is that it just takes too long, and the class will run out of time. But you can imagine what it may sound like. It has a particular set of notes in some population, and it's very different in another population. So these are what they are called dialects. Just like how humans have dialects, birds have dialects as well. So now this is interesting because how do dialects actually form? So it forms because of, it has to form because of learning. The aspect of social learning is very critical for dialects to form. Okay, so that is something that I wanted to kind of stress. And you can see that there is also a component of time. So you can look at this. So these folks had studied this bell bird for about 30 odd years, and so on the x-axis is not the time as in the spectrogram time, but 1970 to 2005, and this is frequency. And you can see that the frequency of whistles have changed over time. Okay, so there is some kind of a drift in the system. We could call it drift, or I don't know if it is selection. But anyway, it turns out that, so the data for that is not here, but long-lived males. So this is just like, again, like in human populations, they say that older individuals often know a lot more individuals, right? Very similar to that, long-lived bellbirds seem to know the songs of many other males around them. Okay, so that means that there is an element of recognition, of individual recognition that's happening with that. So, so two things that come from this is that this idea of learning, song learning, that has an important role in sexual selection, and song dialects are actually a consequence of this. Yeah. Now, I think sometimes it's not very easy to kind of get the idea of dialects. So what I have here is this bird called chirping sparrow, and the song of that. And these are different micro dialects of different individuals. Okay, the bird looks like this. So can you look at this figure and maybe, so what I want you to do is, can you see some similarities or differences? So this is a map, okay, of territories of individuals. Anything you notice?
The neighboring species have similar types of language.
Neighboring individuals. So they are all the same species. These are just different individuals. Yeah? So neighboring individuals have
Similar dialects.
similar. Can you give me an example?
12 and 13. 8 and 6.
12, 13.
8 and 6. Okay.
12
Yeah.
and 13.
12 and 13. Yeah, that sounds pretty good. They're very
20 and 20.
20 and
No, then the opposite.
23. Okay, yeah, kind of. But you're getting, I think most of you are getting the hang of this, right? You can see that the neighbors seem to have elements that are similar. So you can immediately say that there is some amount of learning, song learning that's happening in the system. And I can show you some of the data from this. This is from 26 males in 1997. So if you look at 16, okay, that is the father of 13. Where is 13? 10, 12, yeah, 13. Yeah, but you can see that 13, somebody pointed out 12 and 13, right, being similar. But so, because, so in the system they knew which individual was the father, and so they knew the relationships. So that makes it very easy. So although 16 was the father of 13, 13 actually learnt its song from 12. Yeah? And that's why these two are similar. And you can also look at 8 and 25. Yeah? So 8 is the father of 25, but 25 actually learned its song from 26. You can see that 25 and 26 are very similar, right? So this is actually cultural transmission. So a good equivalent of this would be, let's say that someone. So since we are in the south, you could use a South Indian example, but you could replace this example with any particular area. So someone in let's say the Hyderabad area speaks Telugu in a specific accent or some dialect, but then in the deep south, very close to Chennai, the accent or the dialect is going to be slightly different. Yeah, so this could be you could replace this with Mumbai and Delhi Hindi or something like that. But the point, the connection here is that if you take someone, a young kid from Delhi, and if they move to Bombay, they are going to have accent or dialect which is more similar to where they grew up. Yeah, and that is the idea of cultural transmission. Okay, so it's not exactly genetic. So you can imagine that there's a role of migration also. So here's another example of song variation and dialects. And I mean, you can see that there are different dialects in different parts of the US here, right? In different parts of the range. Okay, so now we're saying that songs tend to be slightly different with space, but how do females know? So there's one element, right? If your song is very different, the females may not even recognize it. Yeah? So you would think that there are some limits to how different the songs can be. So there is variation, and usually this variation increases with geographic distance or some kind of isolation. So like we saw in that map, neighbors can share song types, and as you go further and further away, that may change a little bit more and a little bit more, and then until maybe after quite a bit of distance, the songs are very different. Yeah, so that's something to also remember. Yeah, so in several studies, people have actually looked at genetic distance between populations, and they have looked at how much song varies. Okay, so I hope. So what you need to think about is in terms of the birds. So there's a young bird. What's happening to this bird? It's being fed by the parents, and it basically hears only song from the male parent. Yeah. So if you know a lot of songbirds, they sing. I think someone said that to attract mates. So when it's attracting mates, actually, so there are no chicks at that time, right? So usually, what happens is you have birds singing to attract mates for mate guarding. If you remember from Suhail's examples, and subsequently there is a period of not too much song, and but then later on, when the chick is kind of is out, the male is begins to sing, and up until 3 weeks or so, it hears the song of the parent, but also the neighbors, because the neighbors are also doing the same thing, right? So the chick actually hears songs both of the parent and the neighbors, and then there is this thing called natal dispersal. So I think that was covered at some point. So when an individual disperses and finds territory somewhere else, then it hears a lot more song from other neighbors, not the ones where it kind of grew up. Yeah. So now the question is, the first summer, the first breeding season. By the first breeding season, the bird has to be ready with a song, because it needs to kind of get its act together. It has to kind of attract mates and so on. So the question is, then what song is it going to sing? Given that it has now heard its parent, it has heard its neighbors from, when it was very young, and then later on other neighbors after it dispersed. Right. So this is a very important question that a lot of people have asked. And okay, so I'm just going to, now that you're kind of familiar with spectrograms, I'm going to leave this on the screen, and why don't you tell me what do you think this tells us? So here are the spectrograms, and here are some data from that spectrograms. So this is number of birds recorded and cumulative number of syllable types. So syllable is just, when there are some things that look unique, let's say. Yeah?
The more the geographic area,
Yeah.
the mainland seems to have more variation in terms of syllables as compared to others.
Yeah, that's a really good, so that's a good summary. So basically what it looks like is that in the island, there's not much diversity of song. So this probably has to do with, how much social interaction or learning is happening from the neighbors. Because, if your acoustic environment, what you are exposed to is very limited, then you probably don't develop a larger repertoire. That is one possibility. The other possibility is that you probably don't need much, much of a repertoire, because the number of females, your population density is also much lower, probably. But so this is an important. You can also see this, the kinds of syllables that are not there on the island. So the island has very reduced diversity of song types, okay? And there are other researchers who now point to very similar kinds of things happening because of deforestation, where there is it's called loss of cultural diversity because of deforestation. Okay, so now I'll play a song just so that you wake up and you don't have to shout like a peacock. This is the sedge warbler, and it is the acoustic peacock, let's say, right? So I'm going, and you can try to see if you can, if you can follow through. Yeah, so there's like a lot of, it's very fast, right?
Different syllables.
And there are, lots of kind of different kinds of sounds, and you can kind of make that out. So it's supposed to have like the 70 syllables or something like that. So it's a lot of sound that it's making very rapidly. Okay, that is one thing. There's something called song matching. Now this is a common kind of mistake that people make when talking about duets and song matching. Okay, so song matching is when there is a male that is singing from one territory and another male sings from another territory. So that is song matching. Okay, I think there are equivalents in some musical this thing as well, where you have somebody playing some instrument and then someone else tries to play another instrument and so on. So very similar, some kind of a competition. But this is what happens is that the two males are actually trying to match syllables, so they actually know each other's songs, and they can try and match each other's syllables and add more complexity. Okay, so that is called song matching. What you heard, some part of it had some song matching. There were multiple individuals, if you remember. Yeah. The other interesting thing is that in males there are greater number of syllables. There are relationships with fitness. Okay, they find that those males that have greater number of syllables are actually able to feed young more. Okay, so that is very important, as you may have heard from Maushami's talk also, right? The ability to feed young is an important parameter. They also tend to have less disease. So individuals that have greater song complexity, let's say, and hence the survival, their overall survival is also greater. So these are some correlates with increased number of syllable types. So you can imagine why a female can then use a trait like song to actually kind of, in the sexual selection framework, right? Because if it is an honest signal of male quality, then it works very well for it. It can use songs then to kind of select males. And so what can go wrong in this process? What I mean is that so this bird is just going on vocalizing. What is the cost that it incurs? Predation. Yeah. Anything else?
Energy loss.
Energy. Right. So in fact, the number of syllables is the greater the number of syllables that are there, the more bandwidth that is there, the greater bandwidth that is there, is thought to have very high energetic costs. So in that sense, it is an honest signal of its quality. Okay? So yeah, I'm just hoping I'm not losing track of time. So that's just a few concepts to kind of connect with, let's say, vocal communication on the whole. Now I'm going to talk about the complexity that comes with actually singing in the wild. Okay? And these are things that some of you kind of talked about when we were talking about what happens, depending on the environment that a bird is singing in. Some folks did say that there can be an echo, which is something like this. There can also be, so basically what's happening is, there's this bird that is singing, which is on your left, and you want this signal to reach the bird on the right. But there's so many things that happen on the way. The same sound can get bounced off different objects, from the ground, from leaves, if it's a forest, and so on, right? So you can kind of expect several complications in song transmission depending on the habitat. So here, so you can see this. Remember that I showed you two forms earlier, one in blue and the other in gray. So that's what's happening here, okay? So this panel on the top is when you're actually recording the sound at close range and there is not much loss, okay? So you can see how clear that sound is in terms of amplitude and what spectral features are retained. And now look at this one. Yeah, so in this, can you make out some differences? So I'm talking about B. So some kind of quality, let's say, is gone, but what part of the, so can you see that, the frequencies actually go higher, and that is kind of gone here. So there is some kind of filtering that's happened of the higher frequency sounds. Okay, and remember that when we were talking about sexual selection, we were saying that females tend to select individuals with high variability of song. So things that go from low to high frequency. So if your signal is getting degraded, then I think there is a problem there, right? You are not going to be able to communicate your fitness as well. And then you can also have, different kinds of echoes. Eventually what happens is that the original can be very different from what the bird actually hears, at the end. So remember we were talking about amplitude, about how loud a bird sings, okay? Now, there is some relationship with body size, but there are exceptions because there are some birds that really sing very loud, and there are some numbers there. It doesn't matter. And song amplitude, you can imagine that also correlates with territory size. Yeah, that's fairly straightforward, right? Because you can hold a territory. Because remember we talked about one of the functions of song being territory guarding. So if your neighbor can't hear you, then that's pretty bad, right? So in general, so these are just broad, broad summaries, let's say. The edge, you can hear the song of an individual from the edge of a territory to up to 2 territories away. Yeah, so that's usually how loud songbirds sing. Okay, so here's an example of signal degradation. So this part, right, the one that you hear that kind of sound, that is what is here, and that is what is called trill. Okay, so it's basically one kind of frequency but repeated very rapidly several times. Now the problem is that it degrades very, very fast, like as in it doesn't carry very far. It goes only about 100 meters or so. So there are a lot of studies that show that bird songs have multiple different components. They can have a high frequency part and a low frequency part, and because different parts actually kind of travel differently, they may elicit responses also differently. Okay, so yeah. And not only that, the degradation of song can actually happen in different ways. You can see, so in some ways, longer notes are easier to detect. Alarm calls. So I didn't really talk about alarm calls too much, but alarm calls are very interesting because they are usually very short. Yeah, okay, if you think of most alarm calls, they're really short and not very high bandwidth in terms of frequency. Okay, that's because it takes much longer to to create a sound which goes from low frequency to high frequency. And yeah, and there are also studies that show that alarm calls of multiple species actually can be very similar. So there's something called acoustic niche, where if you were to plot frequency and each species, certain species occupy some acoustic space, and you would find that different species actually have somewhat non-overlapping acoustic niche, okay, except when it comes to alarm calls. So with alarm calls, so there is some kind of convergence in signal there. So many species have very similar sounding alarm calls. And there are a lot of hypotheses about why that happens. There's one that says that it is for interspecies kind of communication, that if there is a raptor which is a threat for some species, other species also kind of takes benefit of that. Yeah, okay. Yeah, so now I want to come back to this question about song degradation. If you remember, rainforests and forested wooded habitats, the habitat is very complex, and that there would be a lot of echoes, there's a lot of reflective surface, there's water, right? And anything else that may be there in the rainforest that can affect signal quality. Yeah, rain, of course. Something else? Humidity. Yeah. And let's say leaf litter. Yeah. So there's a lot of things that can kind of get affected in rainforests. But what's interesting is, more recently, there's this idea in rainforests that there are these acoustic tunnels, and these tunnels are like these gallery kind of things where a lot of birds try and vocalize from, because sound just carries through that tunnel. So if you remember ideas of mixed hunting parties, mixed species flocks, several birds coming together and moving, a lot of species actually follow edges of habitats and things like that, right? So one of the things that a lot of species apparently do is that they seek out these tunnel-like areas where there are clearings for vocalizing, so that the sound carries much further. So everybody's trying to kind of maximize benefit by choosing some of these areas. One other way that you can increase transmission, so the goal is to kind of, your signal, without losing the quality that you're representing in your signal, you want that transmitted as far as possible, right? But then you have energy costs, and you can be predated. There are all these costs that you have to kind of, and there's also, every time that the bird is not singing, it's actually not feeding as well, right? So that's something to remember also. So this is just an image of Sholicola, just because there is a picture. But apart from that, you can think of the idea of how far the bird's song reaches as something called this active space. Okay, so that is the space in which a bird can be heard, an individual can be heard. So what we are doing with these microphones is increasing that active space to the back of this room. But how do birds do this in like real habitats? So one way to do that is kind of you can go to a higher perch, right? So if you've seen several birds, they seem to sing on some perches, right? So, and that is because if you think about this conversion, the amplitude at 40 meters, that the same thing. So at ground, that can transmit to 80 meters. So you can double it by just going from ground to 5 meters. So you're increasing your active space just by going, choosing a song perch that is higher. Yeah. So so that's something to remember. Of course, you have to remember that there are several other challenges with something like this, right? Because there is interspecific competition, so you can't just go to any height, because the other competing species are going to chase you down. So now we come to this idea of acoustic adaptation hypothesis that we started talking about. Like what kinds of sounds travel in which kinds of habitat. So you can see that this is actually a specific bird, the rufous collared sparrow, and what's happening here is that you have these dialects of the same species but in different habitats. Okay, so now, so they are dialects, and what happens is that, so for all the same reasons that we discussed earlier, which is about how songs travel, high frequencies seem to be favored more in open habitats because it does not travel very well in these wooded habitats. So you can imagine that if you go, if you try and think about the species that you've heard, barbets. Anand talked about barbets, right? I mean, he works on barbet acoustics. So those are like forest birds, and you want these sounds to travel really far. And barbets, if you remember, you can hear them really far. As opposed to, let's say, a magpie robin, which is, which has this really nice kind of high frequency kind of songs, but they are more open habitats. Yeah, so I'm going to also, this idea that there is variation, and so what males are trying to do is that they're trying to create this, really, let's say a complex song, or they're trying to increase the frequency modulation, they're trying to get low frequency, high frequency, and you saw that some species were trying to add more number of notes in their song, more syllables, one of the songs that I played. Unfortunately, what happens is that there may be some actual physical limits to what can be produced. And this is one of the biggest challenges in acoustic communication. So it's like you can't have really loud claps, yeah, and you can't do that really fast, because it's just that, the time that it takes to make a loud clap, you have to kind of separate your hands farther and then you clap, right? But if you want to increase the pace of clap, your hand doesn't separate far enough. So these are some physical limits with producing some kinds of song. So, so there's some theory about these birds that have trills, that there is some acoustic space that is just not occupied. So there are no birds that have, like, high frequency songs and which have very frequent, yeah, frequency. Yeah, I hope that's not confusing. So this, I'll just leave this as trivia. There's something called mini breaths. So again, this is it's a physical limitation. So birds can't just endlessly keep, producing sound. They have to breathe in between. And birds have something called mini breaths. So between, and you can see this. So this is a spectrogram, and this is some air sac inflation kind of thing. And you can see breaks there, right? And people have shown that there's a specific gap between sounds that birds need to take. Another similar interesting thing is for a lot of species, when they call, they can elongate their trachea, and that can change a lot of things. What it does not change is the fundamental frequency. It is still producing the fundamental frequency, but by elongating and decreasing the length of the neck, it can change the subsequent, these formants. That is, these other sounds that are created like a step. So that it can change by just elongating and reducing the neck. It doesn't change. It still remains the same. Sorry? Just by increasing the. Yeah, but
This is basically like a closed pipe, right?
I don't know about the closed pipe, but if you were to put the recorder, if you were to measure it at the base near the syrinx, it doesn't change. What the sound when it comes out is when it changes. Yeah. Okay. Just want to say that there are phylogenetic relationships between different kinds of songs. So you will find that, so this is a phylogenetic tree, if you remember from Anand's talk, and there are some relationships. Birds that are more related to each other may sing more similar songs, okay? Then
Songs of the Darwin's finches. Large ground finch. Medium ground finch. Small ground finch. Cactus finch. Small tree finch. Large tree finch. Woodpecker finch. Warble finch.
okay, so the idea of this was to kind of connect back to some of the, the adaptive radiation ideas, the finch, beak, and so on. And you can imagine that just the physical apparatus itself can possibly be limiting to the kinds of sounds that are produced. Okay, so there are a number of various things that interact, but ultimately, when it is used in the framework of sexual selection, there are some common patterns in terms of the number of sound notes or syllables that are produced, low to high frequency that are produced, and some transmission properties that can actually affect this. All right, thank you.